Good to be here. My name is Reuben Budiardja. I'm with the Scientific Computing Group at the Oak Ridge Leadership Computing Facility. And the group that I sit at, the Scientific Computing, we work directly with application, and we are tasked with working on Summit and eventually on Frontiers. Many of us are on the acceptance team for both Summit and Frontiers. So I'm looking at this hardware talk from the perspective of application and how we can best use them. So the outline of my talk today, I'll talk a little bit about OLCF roadmap to exascale. You've heard from Argonne, and we'll take a little bit different path from the beginning, but I think we're sort of almost converging right now. And then I'll talk more about Summit architecture details, and I'll talk about programming environment and how we can use this hardware on Summit. And then I'll give a brief overview about Frontier on what we can say today about Frontier. Okay, so OLCF, our mission is to field the most powerful computer in the world, and we are one of the two facilities, Argonne being the other one of the leadership computing. And we build these infrastructures to facilitate users access to this computer so that we can solve the hardest and the largest problems, anything from the largest structure of the universe in astrophysics and cosmology to the smallest structure of matters in quantum physics and particle physics. And this requires a really large computer to solve. And we also select basically a few time-sensitive problems of national importance that can take advantage of this system. And what's really important is that at the group that I'm with, the Scientific Computing, we partner with this team to help them exploit our machine as best as they can. So the science team, the science project will come to us, and we partner with them so that we help them to tune and get the most out of our machines. So for a little bit of perspective, it's good to look back of where we came from and where we headed. So these are our computers started from the year of 2004 when we have the Cray XE1 Phoenix. And then really from there we have Jaguar, which basically kind of the starting point of the path that we are in now with the accelerated node computing. And Jaguar was the world fastest at the time, and it was upgraded to become Titan on 2012, which was also the world fastest. And that's where we really had large-scale GPU machines on Titan, which basically kind of the first machine with as many GPU as Titan was available. And Titan is to be decommissioned later this year in August. And it's 6 years old in October 2008, so it's almost 9 years old, and it continued to deliver world-class science. And from Titan, we right now have Summit on production, which is currently the world fastest. And from Titan to Summit, we have about 7 to 10x, 10x jump in flops. And we're also right now building Frontier, which will be delivered in 2021, which will be ORNL first exascale machine. So Frontier, we're looking about 50 to 100x performance of Titan. And we're looking at this really not just on the peak flop, but also from the application perspective that hopefully that can utilize this machine. So a little bit overview on Summit. Peak performance is 200 petaflops, and we have a peak 3.3 exaops, what we call it. This is mixed precision or half precision for the analytics and artificial intelligence. So Summit itself sits on about 5,600 square feet, so 2 tennis courts is the floor space on Summit. The system includes about 4,600 nodes. They are connected with dual rail Mellanox InfiniBand, and about 250 petabyte file system at 2.5 terabytes per second data injection. And I'll talk about this in a little bit more details on some slides later on. So each node has 2 IBM Power 9 processor with 6 NVIDIA V100 GPUs and 608 fast memory. And also each node also have an NVMe, non-volatile memory. So the cable connecting Summit is about 185 miles, and so that's a lot of cabling. And it's also cooled by water cooling, but the interesting thing here, I think this is the first system we have that's basically warm water cooler. So with Titan, our previous system, the water have to be chilled water. With Summit, we have about 70 degrees water temperature. So that helps a lot with the electrical bill that we have to pay. So what's exciting is that Summit achieved number 1 on top 500 and number 1 on the HPCG benchmark and Green 500 and the I/O. But this is not as exciting as the application that can use them to solve science, right? This is just benchmark. What's more important about what can we do with this system? Okay, so just to get a sense of perspective between Summit on our previous machine Titan, this slides compare Summit with Titan. So in terms of application performance, Summit gets about 5 to 10x of Titan, and most application gets about 7 to 8x of Titan. So we have many fewer nodes. So Titan have about 18,000 something, almost 19,000 nodes, and Summit have 4,600 nodes. But these nodes are much more powerful nodes. So Titan nodes is 1.4 teraflop, while one Summit node is 42 teraflops. So application has to figure out how to really exploit these nodes, to program these nodes and use it efficiently. Titan does not have NVMe, but Summit has about 1,600 gigabytes for each node. Has a lot more total memory and better interconnect, faster interconnect. We moved from 3D Taurus to non-blocking FAT3, and also processor. Titan has 1 AMD Opteron and 1 NVIDIA Kepler, while Summit has 2 IBM Power 9 and 6 NVIDIA Volta. And we have a lot more file system. And what's interesting here is that you get 7x performance for slightly more power. So Summit rated theoretical peak is 13 megawatts of power. Mostly we've been running about 8 to 9 megawatts. So we haven't really measured anything close to the theoretical peak or theoretical power consumption peak while running large application on Summit. So just with slightly more power, we get 7x more performance on Summit compared to Titan. And that's really the advantage of using or having a lot more GPU, which are really power efficient. This is a picture of Summit board, and you can see the liquid cooling here on this pipe. We have the PCIe slot and the power supply and the 3 NVIDIA Volta on one socket and the other 3 on the next socket, and the Power 9 processor. But probably more useful is to look at this schematics, and I'll walk through this also. And by the way, if you have any question during this talk, feel free to interrupt and ask them now. You don't have to wait until the end of the talk. So on one side, we have Power 9 connected by NVLink. Those are 50 gigabytes link with all the 3 GPUs. So all the 3 GPUs are connected with this 50 gigabyte green arrow links. And each GPU has what we call high bandwidth memory, 16 gigabyte, and they're connected with high speed 900 gigabyte per second memory. Between the two power, so this is like one side, and then on the other side of the socket is the same thing, and they're connected with 64 gigabyte XBus. So from application perspective, if you program this thing, you have to think about NUMA effect and placement, where you want your GPUs to be and where you want your processor and your process to be, because you probably don't want to go across this small 64 gigabyte XBus. Each of the Power 9 is connected through the 170 gigabyte per second DRAM, which its DRAM has 256 gigabyte. And they are also connected to the NIC, 16 gigabyte per second. That's the orange arrow here. And the NIC goes out to the network at 12.5 gigabytes. There are 2 physical ports on the NIC, and to get the total 25 gigabytes the bandwidth to the network, you have to use the 2 sides of the sockets. And each of the node also connected with the burst buffer or the NVMe with 6 gigabyte reads and 2.1 gigabyte writes. Okay, all the memories in the nodes are memory coherent, and this is all, again, this is the same schematic, just slightly different perspective. Here I see that each CPU has, 22 cores, and each core actually has 4 hardware threads that you can utilize that can run separate processes. So the 22 cores, 1 core per socket is reserved for operating system. This is to minimize jitters due to operating system activities. And the same thing on the other side. And let's see, we can put in, or you can run job in 3 different SMT modes. You can run in SMT 1, 2, or 4, and that's controlled by your job request. So by default, we run SMT4 because we see, even though you don't necessarily use 4 threads, that seems to be giving the highest performance. But you can pick what you want at job submission time. So a little bit more details on the Power 9. So this is 2 cores of Power 9, each core running 4 hardware threads. They have their own L1 cache, but the 2 cores shares the L2 cache and share the L3 cache. So if you're running 4 processes or 4 threads on each core, just be aware of this and the memory contention that might be happening if you utilize the higher level cache. And a little bit about the NVIDIA Volta V100. We have about 27,000 of them on Summit. We have the version that built for NVLink. So the peak is 7.8 teraflops for double precision, 15.7 for single precision. And again, as you showed, each of the card is connected by NVLink, capable of 300 gigabytes per second bidirectional bandwidth, and they're connected to the high bandwidth memory, 16 gigabyte high bandwidth memory with 900 gigabytes per second. So these numbers are peak numbers, and it depends on your application, how close you can get. So one thing that's new on this Volta is the introduction of this tensor cores. So basically, the tensor cores do a half precision multiply at 4x4 matrices, and they accumulate into either half precision or single precision matrices. So if you can formulate your problem to take advantage of this, it will automatically go to the tensor core, and you get benefits of using them. So this can goes up to about 125 teraflops. So we have 640 tensor cores on each Volta. And so basically the question here is how you can utilize this. And this is research questions, and some success has been done. For example, there's a paper on last SE18 coming out from the ICL team at UT, where they can do mixed precision and achieve about 4x of what they can do just using the regular cupolas. Also, this I encourage you to take a look at this paper, if you will. This is one of the winner of the 2018 Gordon Prize from ORNL, where they were able to achieve about 2.3 exaops by basically changing their algorithm to utilize this tensor cores and do mixed precision computation to get better results than they can do with just using the regular matrix multiplication using cupolas. So this is a simple benchmark, a stream benchmark. So basically benchmark we do so that we can understand what we can actually see from the application perspective and help us sort of pinpoint the pain points that we may be experiencing. So stream benchmark just basically, Scott talked about this a little bit, comparing 4 operation on peak is just basically 1 cabinet of Summit is our test and development system. On peak, we can get about 82% of the fraction of theoretical peak. This is to compare it with on Titan. Not only you get much higher number, but you also achieve a higher fraction of peak. And on the GDDR bandwidth, this is on the GPUs, you can get about 92% of theoretical peak, while on Titan with the Kepler GPU, you get only about 72% theoretical peak. So higher theoretical bandwidth, but also higher fraction achievable by application. So you do get runtime variability up to 9%, and this is a result of about 1,000 tests. So similar thing, this is testing the end filling rate from core 0. So if you have the process on core 0, you go to GPU 0, 1, 2, 3, 4, 5, from host to device and device to host. 0 to GPU 0 to 2, that's the closest to your socket. So that's on the same side of the socket. You get very close to theoretical peak. But as you go to across the socket, you have to go through this X bus, so you get lower performance on GPU 3 and 4 and 5. Also on the bidirectional, so you get almost the sum of the 2 end filling. You also so this is limited by the X bus that you have to go through when you go to GPU 3 and 4 and 5. So this is the NUMA effect that application needs to consider when they're using across. We don't see this as the most use cases for the application will employ. This is similar, except right now you distribute the ranks equally across socket, and in this case the access is more, it's not limited by the X bus because everything is local to the socket, so you get much better performance. And again, this is just testing from socket 0 to socket 1. And again, this is illustrate the NUMA effect that you need to consider if you go across the socket from, from the first to the second processor. So Summit network is a non-blocking tree. The 2 new features on Summit is that it has adaptive routing, which enable you to bypass congestion. So in this case, a package might arrive out of order, and they load balance at each switch. We also have sharp. Basically, the network built fancy trees so that you can reduce some collective operation. And small collective will be able to utilize this and get much better latency across the network. So again, I mentioned that there are 2 physical ports on the NIC that you have to use to be able to get the full 25 gigabyte per second. And the two physical ports is basically split into 4 virtual ports, and you can tune the MPI so that you can either stripe to optimize for bandwidth, or you can use them both to optimize for latency. And there are many, many more tuning also for sharp that you can use that I don't have time to discuss here, but you can look it up on our website, and there's some training to introduce that. Okay, we have parallel fast system is mounted, and this gives you access to the same space across all the nodes. It has 2.5 terabytes per second aggregate, but we also have node local NVMe, which basically give you access just within the job on that space. So this is not shared across the nodes, but one thing that you can consider if you look at this plot, if you use more and more nodes, then the bandwidth per node will decrease if you use the parallel file system because they are shared across the network, but you get linear bandwidth across the nodes with NVMe because they are local. So this is something that you can consider if your application has a lot of read or write that you can do locally on the node. Then this is a burst buffer, that's something that you can use at the end of the job. You need to drain them to the parallel file system because they will be no longer accessible to you. We have tools to do that. We have libraries to do that. You can do them manually. A little bit about the programming environment. So we have 4 compilers with LLVM only support C and C++ at the moment. We support CUDA, CUDA Fortran, OpenMP for offload, and OpenACC for offload on some of the compilers. So with PGI, you can do CUDA, CUDA Fortran, and OpenACC. With GCC, OpenMP, we've tested. It's basically only functional and not performing yet. With IBM XL, if you want to use OpenMP for offload, then we have IBM XL that will do OpenMP and CUDA Fortran and CUDA, but will not do OpenACC. So these programming models is depending on what you pick, you may be stuck in using 1 or 2 compilers on Summit. So we have a variety of debugger and performance tools, just comparing it from Titan for what we have on Titan and on Summit. So we anticipate most applications will be able to use what they've been using before on Titan to Summit with few transition. And also this is just a list of numerical library available on Summit, and that can be used as building blocks to build more libraries. And I will not go into details on this. And so one thing that Summit introduced is the new job launcher called JSRun. Basically, JSRun lets you provide abstraction of a node with the concept of resource set. This is motivated by the fact that Summit nodes are so powerful and so large that using it might be from the get-go a little bit complicated. So resource set, basically you tell the launcher how you can abstract the node by telling it what you need within a resource set. So you can assign a number of CPUs and GPUs within a node. Under the hood, it's using the C group. And you can assign how many MPI processes with threads and manage placement. So this lets you do node sharings, multiple executables within a job. So node sharing with yourself, basically, not with other user. So for example, you can have a job that has GPU heavy computation, and so you're leaving a lot of the Power9 idles, and you can run within the same job, data analytic job or post-processing job behind it, and using this abstraction to do while your application only assign GPU resources and your data analytic job, you assign only the CPU resources. So I have some more example about this on how we're using the node. So programming multiple GPUs, so there are multiple paths, right? Each with different level of flexibility and sophistication, depends on how much manual and explicit control you want to use in your application. So the simple model, you have 1 MPR, 1 thread per GPU. You can also share multiple MPIs or multiple threads on a single GPU. This is if your application does not utilize your GPU enough, then multiple processes sharing GPU might increase your GPU utilization. So in a sense, you become more efficient in using the GPUs. Or you want to expose the node level parallelism directly, where you have multiple processes, multiple GPUs. This is where it gets more complicated, where you have to manage your placement and GPU binding and everything within the application. But it gives you more flexibility in terms of your data movement and everything. So here's an example of where we can use 1 GPU per MPI rank. So in this case, your summit nodes becomes more like 6 Titan nodes, right? Here I showed that this process 0 binds to the 6 or 7 core of the Power 9 and bind to the first GPU and so on and so on. So every application or every process only see a single GPU, and the launcher lets you do this by basically say for every process assign 7 CPU, 1 GPU, and 1 task. And so if the application is transitioning from Titan, this is almost basically compile and run using this model without worrying about their multiple GPUs on a summit node. And furthermore, you can use threads with OpenMP or pthreads to utilize more of the CPU cores. But just to be aware, the CPU makes up only small percentage of the flops. So about 3% of the flops coming from the GPU, from the CPU. This is similar, except now we have multiple processes sharing 1 GPU that I mentioned before. This is to increase GPU utilization if your single MPI rank cannot fully occupy a GPU. So this is enabled by the CUDA multi-process service or CUDA MPS. Be aware that if you do this, there could be more communication congestion because now you're sharing a lot of the communication infrastructure, but you have a lot more processes running on a single node. So this is probably one of the most commonly used approach with 1 GPU per MPI rank, but its rank is threading across multiple cores, right? So this is showing 7 threads for every MPI process, and this assumes the similar amount of work distributed across all ranks, and you may leave some cores of GPU unused. But this is pretty straightforward model still. So you can also do where you have 1 rank on the first socket and another rank on the second socket, and you control the GPU binding. Now you have 3 GPU per process, and you have to manage them and how you want to distribute your job across the 3 GPUs. And basically communicate across the socket. You can do this with explicit control, where with OpenMP or with OpenACC, for example, you can use the ACC set device num, or with OpenMP, you have the device num clause. And with CUDA, you use the CUDA set device routine. And a lot of people do this manually. A lot of our power users do this manually, or you can do this with implicit control, where basically eventually the compiler and runtime might break up your large tasks across multiple GPU automatically. I don't think this is doable yet at this moment, but there are task-based execution models in development that can do this, and there are multi-GPU aware libraries that can do this, basically distribute your tasks across different GPUs. So in the last 10 minutes, I'll talk a little bit about Frontier. This will be delivered in 2021, we hope, and this will be Oak Ridge first exascale machine. This is a partnership between Oak Ridge, Cray, and AMD, and we will have peak performance greater than 1.5 exaflops, and we will have more than 100 Cray Shasta cabinet connected by the SyncShot network. Again, we also have adaptive routing. We have quality of service and congestion control. We use an AMD EPYC processor with 4 Radeon Instinct GPU connected purpose-built for this machine. They will be connected with the high-speed AMD Infinity fabric. They will be coherent across the node with 100 gigabyte per second injection bandwidth, and we also have near-node NVMe storage. So to compare between Titan, Summit, and Frontier, from Titan to Summit, we go about 10x, and from Summit to Frontier, it will be about 7.5 x, and the same number of cabinets, we think, and this is still not sure yet, but we will have AMD EPYC on Frontier with 4 Radeon GPU, and AMD Infinity Fabric on the node with Cray Slingshot network, and we're also going to be using the Dragonfly topology, and it will be 2.2 to 4x performance on the I/O compared to Summit. Okay, so there's some question earlier about programming environment and what will be supported or what will be in the future, and so this is our take on it. We will support OpenMP basically as the supported programming model on Summit or on Frontier, and we will be moving from CUDA to HIP on the AMD system. HIP is a compatibility layer or portability layer between the AMD ROCm libraries and the NVIDIA CUDA, and we will have the GCC, the Cray, and the AMD ROCm compilers on Frontiers, and rather than using CUDA, I mentioned we're going to be using HIP and C and C++. So if you are using CUDA Fortran at this moment, then we'll have to transition either with Fortran and with HIP and HIP C or C++ or using OpenMP. So we think transition from OpenACC to OpenMP will be relatively straightforward. There's some discussion about whether or not we can support OpenACC directly on Frontier, but that's to be finalized yet. So Summit is now a premier development platform for Frontier. We will be having HIP on Summit so that people can start transitioning toward moving to Frontier with AMD-based GPU. Okay, so I mentioned that HIP is an interface for portability developed by AMD to write portable code between AMD and NVIDIA GPU. Under the hood, if you compile to NVIDIA GPU, it uses CUDA, and if you compile to AMD GPU, it uses ROCm. It has very similar API to CUDA, and AMD has developed these HIPify tools to help you convert from CUDA written code to HIP, and we will make this available on Summit so that people can start experimenting and running with this model. That's the end of my talk. I want to put acknowledgement for the rest of my team. There are a lot more info on Summit that you can look up on our user guide, and also we done a good job in archiving most of our training, so you can go to our training archive and browse the slides and video. And from the training archive, this is a paper published in SC18 Proceedings that talks a lot more about the hardware on Summit with all the benchmark and everything. So with that, I'll be happy to answer any questions you may have. Thank you.
So you mentioned the CUDA MPS. I've been working on a different AC922 system, and I noticed that depending on how you launch MPS, you get a huge difference in scaling within the single node. So I was wondering if there's any details about how you deal with MPS on Summit.
So yes, that's a good question. So we've seen that also that you can run more than one MPS. So we actually support that. By default, we only run one MPS for every job that you request on every node. but you can request that you run 2 or 4 MPS, I think, on the node. And some application has seen differences in performance depending on using 1 or 2 MPS. But there's no straightforward answer, unfortunately.
Hi, thanks for the talk. So I just had a question on, the previous talk was Aurora having an Intel discrete GPU system, and this is AMD. So I was curious, was it deliberate that 2 exascale machines running at the same time have very different programming architectures compared to whatever is there now? Can you comment on that?
Yeah, so I think one of the goal of having 2 leadership computing facilities that we provide the first architecture on the system that we provide. So that one of the reason, and then it just happened that on our case during procurement, we find that this will be the best system for us, and Argonne found that the Intel system is the system that they pick. So diversity is on our minds, obviously, and so that to provide diversity to application also.
So just compare with Argonne, I guess, transition from Summit to Frontier sounds like a lot less work for the programmers than, let's say, the same for Argonne. Is that right? I mean, other than, of course, you get different chips from different manufacturers and all that. But overall, you go from the same CPU, GPU to the CPU, GPU.
Yes, in some sense that's correct. We basically changed our GPU vendors, but on Oak Ridge, if you've been on the Oak Ridge machine, then you basically has been on this path of this accelerated computing with having a CPU and have to manage CPU and GPU. So yes.
For the NVLink and PCIe comparisons of performance, do you know how many GPUs you needed to use to see that kind of difference in performance? Because we tried doing it with 2 GPUs and 4 GPUs, and we didn't see much of a difference.
So with just 1 GPU, you should see the different data transfer rate between your host CPU to the GPU with NVLink versus PCIe, right? So with NVLink, it's so surprisingly, it's fairly easy, I would say, to get close to peak performance with NVLink. So I show you the result from the stream benchmark, but even just with we've tried with just OpenMP target update, for example. Just as simple as that, we get fairly close to 40, 45 gigabyte per second transfer rate, which is so yeah. With I think with 1 GPU, you should already see the differences in terms of transfer rate.
Oh, I think I posed the question incorrectly. What I meant was using GPU Direct as a communication across GPUs versus just doing GPU to host and host to host, and then the host to device. So if we use GPU Direct to communicate data directly from GPU 0 to GPU 1,
yes,
versus if we go through the host.
Yeah, so that's if you go with GPU Direct, then you can go directly, and you should get much better performance as long as you on Summit, as long as you stay on the same socket. If you go through on the next socket, then you see the NUMA effect because you have to go to the host and through the X bus and then through the next GPU on the other side. But with GPU Direct, since it's all connected through the NVLink, you should see close to peak also.
Thank you.
We can talk later if that doesn't answer your questions. Question over there.
Frontier support OpenCL?
I'm sorry, say again?
Will Frontier support OpenCL?
We don't know yet. That's not, unfortunately, not something we can answer right now. But yes.
Do you have a sense of what sort of CPU-GPU ratios people are actually running their jobs on Summit with?
Yeah, so most people, almost everyone on Summit runs with some kind of GPU acceleration. And so part of our review for application that gets accepted on Summit is how ready they are in using using the GPU, or if they need a little bit more help to get them so that they can utilize GPU. So most of our users are using, for the production job, are using GPUs on Summit.
But like what, so are they using all 6 GPUs and
Yes.
all of the CPUs, or like what sort of?
There are a lot of, I think the most common use cases is probably using 6 of the GPU and maybe 6 MPI per node and using some threadings. But then again, even if you're not using all of the power cores, Power 9 cores, I don't think we really care that much, right? Because that makes a really small fractions of the computational power.
So looking at the comparisons between Titan and Summit, you have about 5 to 10 times the performance on Summit versus Titan, but the bisection bandwidth on both of them is about the same. So do
Yes.
users end up seeing a big bottleneck from that?
Yes. There are some applications that are communication heavy that seeing more bottleneck on that. So communication is always, communication and memory bandwidth is always a problem. So yes, that's true. So that's something that application has to figure out. If you can, even if you have to probably redo some of your computation, it's probably still better than to try to communicate across the network, right? Because you can think of flops is basically free, data movement is expensive. Okay, thank you very much.